So welcome back. So now we open the session on shareable HDL cores. So we are going to listen 5 presentations. So the first one is given by Lucas Vick. So Lucas got his Master of Science in 2014 in Applied Physics at the Linköping University in Sweden. He's been working as an FPGA designer for 10 years in automotive, defense, and communication industry. And most of that time, he was an entrepreneur. So he has run 3 companies developing FPGA-based products, consulting, and freelancing. So he's currently living in Austria. So Lucas, we open your presentation.
Great, thank you so much. Hello everyone, my name is Lucas Vick, and welcome to this presentation about clock domain crossings in FPGA. Before we get started, I would like to extend my thanks to Davide and to the rest of the committee, wherever you are, for inviting me to this conference. It is of course a big honor to be invited to CERN, not something that I can say no to. And thanks to all of you for choosing to attend my presentation here today. I sincerely hope that you will find it interesting and that you will learn something and that it will be useful for you. Before we jump into it, let's say a few words about me. Actually, Matthias said almost all of it. I'm 34 years old. I live in Austria, in beautiful Vienna. But I'm from Sweden originally, from beautiful Nyköping, which is not so bad either. I have a master's, Matthias said this. I've been working with FPGA development for 10 years as an entrepreneur most of the time, a few different businesses, but currently in Vienna I'm working as a freelancer in software and FPGA development, remote most of the time these days. And lastly, apart from my work, my claim to fame is that in spring 2024, I started writing this article series that I'm publishing on LinkedIn, where I talk about CDC, and specifically I dive into how do we need to apply timing constraints to make the CDCs robust. And this is probably the reason that I ended up here, and it's probably the reason that some of you out there know me. So yeah, this is a 40-minute session, which means that I will be talking for 30 minutes. And then at the end, we have a dedicated slot for Q&A. And I would highly encourage you to ask any and all questions that you might have. If you want to ask them at the end, or if you want to talk one-on-one or have deeper discussions, you can catch me at any point during the conference, of course. So just ask any questions, because this is a complicated topic, and it's absolutely okay to have questions. But why is it a complicated topic? Why is CDC so hard? Well, a handful of things, I would say. I would say that the topic of CDC is an underexplored area for many people and for the FPGA space in general, I would say. I think for a lot of people, CDC, it remains in this kind of shadow realm where we kind of understand it. We kind of know how it works. We kind of know why it works. Maybe our company has some CDC blocks in place. We use them. They seem to work. And if it works, and that is great. But I just think that as scientists and as engineers, we would like to have a more robust and rigorous understanding of the technology that we work with. I think people like us, we just feel better when we have a deep and bottom-up understanding of things. And that's why we're here today. But let's stay on this question, why CDC is so hard. The first reason I would say is that, to me, or to my understanding, CDC is very hard to verify. Because when we're talking about CDC, we get into these more analog or asynchronous aspects of FPGA design. And what I mean by that is that when we're working with normal synchronous digital designs, we get a lot of guarantees from the implementation timing engine that when we write a value to a flip-flop, that value is going to be a stable, 1 or 0. And when we read that value, it's also going to be a stable value. This is setup and hold analysis. But when we're doing CDC, when we're going between different clock domains, there is no setup or hold analysis because it's not really possible. So instead, we need to think about things like propagation delay and rise and fall times. And these are analog terms. And what is worse, these things, they vary depending on which FPGA individual we are on. They vary with temperature, they vary with humidity, and depending on the radiation situation, we might get different events, different behavior. Say, for example, that you're working on an FPGA design, it contains some CDC, and the constraints for this CDC are not so great. You build it, you get your bit file, you upload it to the device on your desk, and you run it, and it works. It's all good. But then your colleague, 3 desks over, he runs it on his device, and it doesn't work. And these are the things that can happen when we're working with CDC, and the constraints are not so great. Maybe this CDC topology, whatever it is, maybe on your device, the latency for the signal to pass through it is 2 clock cycles. Maybe on your colleague's device, maybe your colleague's device has been running for 10 hours. Maybe it's hot. Maybe on his device it's 3 clock cycles. And this could be the difference between functionality and a bug. And this doesn't mean that there's anything wrong with the RTL. It's just that the constraints are not good enough. But what we want is for our designs to be safe and robust and reliable under all conditions. And we also want some kind of predictable behavior, like some kind of determinism in our builds. And a second. And I would claim right here and now that the fact that you built your design with CDC and you tested it on your device and it worked once is not a proof. It's not even an indication that it's going to work on all devices under all conditions. Because these things vary with the different variables. So I think like these factors, it necessitates a radically different approach, a radically different process when it comes to verification and also the design process of CDC compared to regular synchronous designs. Next reason CDC is so hard is that I find it very hard to perform information gathering on this topic. So when you Google this, you get very few hits, very few articles, in my opinion, at least relative to how important the topic is. And the few hits that you do find, I would say that they all suffer from a limited scope. What I mean by that is that they spend a lot of time talking about the RTL construction of things, but they spend little to no time talking about usage constraints or timing constraints or how this CDC is made reliable, which would be the most important thing for me. And I would say, just in general, there's an incredible amount of bad advice out there in this area. Dangerous, counterproductive advice. A lot of it from third parties, but sadly, unfortunately, a lot of it comes from the FPGA vendors themselves. I wrote an article about this. Yeah. As sad as that is to say, like it's in their forums, definitely, but also in the official user guides and official documentation. So yeah, it's quite regrettable, and I mean, no wonder the topic of CDC is confusing to so many people when that is the case. Third reason why CDC is so hard, you cannot see it. This is a huge slide. So what happens when you sit down and think about this, like when you break down all the different combinations of factors, all the different situations that you need to take into account, all the different possibilities, you end up with this huge space of different scenarios. So we have, for example, oh, sorry, that's the wrong clicker. Here we have the pointer. For example, we have just a few typical signal types, and these are like the classic, the regular CDC topologies. These map to the classic CDC topologies. We also need to think about, depending on the application that we are in, we have different requirements about data qualification, where sometimes we want to send data through back to back as soon as possible, whereas in other cases, we need to have some kind of handshaking scheme, axis stream, where the receiver has an indicator where it's ready to receive data or not, and the sender has an indicator whether it has valid data or not. We also need to think about throughput, where in some applications we require to be able to send data every single clock cycle, whereas in some applications it's okay if we are able to send data every 6th clock cycle, for example. And with these scenarios, you can optimize in different dimensions, usually resource utilization, depending on the requirements of the application. We also need to think about the clock relationship, where can either be asynchronous or synchronous, where asynchronous is usually what we mean when we say different clocks, just two unrelated clocks, or synchronous, meaning that one clock is kind of derived from the other one. And these two scenarios open up for different possibilities. We also need to reflect on what happens depending on the clock rate relationship. Are we going from a fast clock to a slow clock, or from a slow clock to a fast clock? Where typically, of course, fast to slow is quite problematic because we're going from a higher bandwidth to a lower bandwidth. And finally, it's worth reflecting on the clock behavior. Depending on what clock we have, it might be possible that the clock stops at a seemingly random time. And what happens then? What happens to our circuit? Can it recover from that? So yeah, this is just to illustrate that there's a whole lot to think about, and there's like a huge space of different scenarios that we can end up in. Yeah, moving on. Last slide about this, why CDC is so hard, and I think this is the most important one. CDC is so hard because we spend so little time working on it. I mean it, how much time does the average FPGA developer spend per year constraining, constructing CDC, or even studying the topic? Maybe 8 hours, maybe even less. And I think that's the real problem, because, I mean, for me and for most people, I think the way we learn is that we learn by doing. We need to write a lot of code, we need to try different things, we need to evaluate, we need to do some mistakes along the way, and that's how we learn. But yeah, I think that's just not how the typical workday looks for the typical FPGA developer. So that's why CDC, it kind of remains in this half unknown state. But okay, I spent a couple of slides talking about why CDC is so hard. And this all, it leads to a very relevant and very justified question, which is, if CDC is so goddamn hard, then why should you listen to me about it? Who am I to talk about this? What gives me the right? And the simple answer to that is nothing. I have no special qualifications, no formal education or certification in this area. I would simply say that I am a very experienced developer who has spent a lot of time thinking about these things. I took a personal interest in this topic a couple of years into my career, and since then I've thought a lot about this. Like, I've looked at what are other people doing, I've tried out a lot of things, I've evaluated a lot. So yeah, overall I think I've put more brain power into this topic than most. So I have some knowledge in this, but Even still, I would encourage you to not just take my word for it, but to instead keep an open and critical mind, because I am the first to admit that I'm just one guy, and this is a very complicated topic, so I need peer review, or as we say in industry, code review, which is the idea that two heads think better than one. And if we extrapolate that, it means that 15,000 heads think better than one. And this is my whole idea, my whole strategy behind this, that I want to put everything out there for the scrutiny of the public. I want to publish all my work. I want to publish my thinking and my reasoning and my motivations. And I want to publish it in front of as many smart and critical minds as possible. This is why I put the CDC blocks that I have written. They are on GitHub, open source to anyone. Anyone can use them. Anyone can look at the code. Anyone can analyze it, try to find weaknesses. Anyone can make suggestions. Anyone can make bug reports. This is also the reason that I'm writing this LinkedIn article series, where I try to break down the different topologies and discuss what constraints are needed to make them robust under all conditions. And these articles I checked some days ago, and they have, as of now, around 15,000 views. So that means that 15,000 sharp minds have read my ideas and put them to the scrutiny of their understanding. And there have been conversations in the comment section where I have definitely learned things in this, and I have shifted my own perspective in some areas, which is great. I'm super happy about that. That was the whole reason for doing this from the beginning. And I think that's just good scientific process. We put our ideas out there for scrutiny of the public, and good ideas will prevail and bad ideas will die. I think that's great. That's how it's supposed to work. But okay, let's get into some actual CDC circuitry. And I would like to start this in the form of a small quiz. So I want to ask you the simple question: what is wrong with this CDC? So this is a single-bit semi-static level CDC. It's the classic, most simple one, the textbook. We have this double flip-flop chain in the receiver domain. And in this case, it is driven by two signals from a flip-flop going through an XOR LUT, which then crosses the clock domains into the flip-flops. So what is wrong with this? How can this fail? What is the problem here? If you read my articles, you know the answer. It's fine. I can answer for you. What do you? Yeah?
I would put a register after the XOR.
Yes. Thank you. Thank you.
Repeat the answer for the...
Yeah, absolutely. Absolutely, I will. And I will answer it in more details. But yes, the correct answer is that we need to insert a flip-flop here. And let me illustrate why this is a problem. If we imagine the scenario that both A and B are 0, which means that XOR result is 0, and then in the next clock cycle they both toggle to 1, which means that XOR result should remain 0. It should always be 0. But given how an FPGA works with routing delays, we are pretty much guaranteed that A and B will not reach the XOR LUT at the exact same time. There will be some time instance where one of them is 1 and the other is 0. We are pretty much guaranteed of this. Which means that for some time instance, the XOR result will be 1. Maybe not a stable one, maybe it's just glitches and transients. But if we are really unlucky, these glitches and transients can be sampled here, meaning that an erroneous value of 1 can be sampled, which means complete failure of this CDC. So what we need to do, as the gentleman correctly pointed out, is that we need to insert a flip-flop. So what will happen here is that setup analysis will make sure that the value is sampled here only when it has reached its steady state, when it's a stable value. And then we can just simply read it in the receiver domain. Next one. This one is more complicated, but the question is still simple and the same. What is wrong with this CDC? So this is a multi-bit CDC. This is what we call the two-phase handshaking CDC. This is a free-running variant of it. So we have a multi-bit data input that is sampled in the source domain, and it's then allowed to propagate to the receiver domain where it's sampled again, and then all the data bits are output in parallel. And it's controlled by this free-running single-bit feedback loop where it's a single bit, it's a level value that will go all the way through the loop and back, and then it goes to this inverter. So the value will toggle, and then it will loop all the way around and back, and then it will invert again and toggle and go round, round, round. And we have these flip-flop XOR sub-circuits, and these are level-to-pulse circuits. And what they do is that when the value here switches from 1 to 0 or 0 to 1, for one clock cycle, the XOR result is 1. And we will clock enable and sample a value here, which will propagate. And while that value is propagating, the level value will propagate through flip-flop and flip-flop, and then same circuit here. XOR value will be 1 for one clock cycle, clock enable, and we will sample the parallel bits, and we output them. And this will go back to back to back to back. So what is the problem here? Anyone know it? I haven't published this article yet, so it's a little bit harder. There are two problems here. The first one is exactly the same on the previous slide, where we are driving. Oh, sorry, wrong button again. There we have the pointer. We are driving this crossing with a LUT, which is, in general, I would say a bad idea. The FPGA vendors, they make no guarantees about the electrical characteristics of a LUT, what their glitch properties are. So exactly as on the previous one, where we had to insert a flip-flop after the LUT, we have to do the same here. The second problem comes from the sampling timing, where imagine that a toggling level value comes here. And to illustrate this, I would like to imagine that clock 0 is 50 times faster than clock 1. And we get a toggle level value here, so we will trigger the XOR, which for one clock cycle will put a 1 here, so that at the next rising edge, we will sample data here. But while we are waiting for the next rising edge, the level value will be fed back here. It will go through one flip-flop and two flip-flop. And since clock 0 is 50 times faster, it will reach here and it will trigger this XOR. And it will trigger a clock enable, so that while this part of the circuit was waiting to sample data, which was presumably stable, like that is the contract of these two handshaking. While this one was waiting to sample data, we are already sampling new data over here. And we will do it many times, actually, given the clock, like the more extreme clock rate relationship. So this simply doesn't work at all. Like the structure falls apart completely. What we need to do is quite simple. We need to insert more flip-flops in the feedback loop. First one here, which makes sure that this LUT is behind the flip-flop now. And overall, we have made it so that there are now 6 flip-flops in the feedback loop rather than 4. And now we don't have this timing problem anymore. We will only sample data here when it's stable. Like, we will not sample new data here before it has been sampled here. So it is always stable and the CDC works. But a very fun thing to notice here is that the way the circuit looked on the previous slide, it would have worked perfectly as long as the clocks are quite close to each other. But in order to make it robust in all cases, in all clock rate relationships, we had to insert so that we now have 6 flip-flops in the feedback loop versus the previous one where we only had 4. And this number of flip-flops, it correlates directly with the latency of this CDC and also the sampling interval, which means that in order to make this CDC robust and reliable, we have also made it worse, where we have higher latency and we have lower throughput now. But yeah, these are the kind of trade-offs that we have to make sometimes, that we had something that worked in certain conditions, but in order to make it reliable under all conditions, we have made it worse, and we are also consuming more resources. So, but yeah, it's reliable, and like for most people, for me, definitely that is the most important thing. So, but yeah, it's fun thinking about these trade-offs. But okay, I think now is a good time to introduce the hdl-modules open source project, which is where the CDC blocks that I have written are available. So you have a link to the website where there's documentation, and also to the GitHub where there's source code, of course. I started this project back in 2017 when I had just left my first job. And I was sad at this point. I was sad that all the good stuff that I had written at this job, it was left there. It was left behind closed doors. And I was philosophizing a bit, and it didn't make any sense to me that all the different companies out there, they spend their own precious time and resources to do in-house development of things that are completely generic, things that have nothing to do with their IP or their product or their business, their customers. Completely generic things like FIFO implementations or CDC blocks, just as an example. So what I started doing is that since I started this project in 2017, everything that I write that is not company specific, everything that is generic, I committed to this GitHub repository instead. And for many years, I had to do all of that in my free time, unfortunately, but with time, I was also able to do it in company time, which was nice. And with time, 7 years, it has, of course, grown to be quite a big library of very useful things. Like, I use this every single day in my work. And I've put a considerable amount of effort in order to make everything as high quality as possible. Like, everything is reviewed, everything is well tested and well documented, because I want it to be useful, and otherwise there is no point to it. Yeah, so it's quite a big library. You can explore it on your own, but for the topic of this presentation, which is CDC, I want to mention that there are a number of CDC implementations, quite a few, for the classic, very common topologies, but also for some of the more exotic ones. And I would say that these CDCs, they have been developed in quite a rigorous environment, I would say. They all come from an environment where I've had a lot of discussions with my colleagues about it. They have all been, they are all, how to say? Sorry, I kind of lost myself. Yeah. Yeah. Like I said earlier, like discussions with colleagues, but also like I've been studying these topics a lot, reading articles, looking at what others are doing. I've been writing a lot of code, synthesizing, evaluating, looking at what did the tool do with it, trying different types of constraints, trying to express the constraints in different ways. Again, synthesizing, evaluating, see that the constraint actually worked, things like these. And yeah, just as with the other, everything is reviewed, everything is documented, everything is well tested in simulation. And for the CDC blocks, they're also all of them tested on device to show that they functionally work. So yeah, they're quite good. You can find them if you go to the GitHub and you click on the modules folder, and then you click on the resync, and then you end up in this source tree where you have a source folder, which is where all the RTL is, and you have a constraints folder where constraints are and tests and other things. You can also find on the website, once again, if you click the resync, you end up on a page like this where you have some figures, some block diagrams, some notes. Here you will have links to my LinkedIn articles where for each of these, or some of these at least, I break down how the constraints work and how the constraints ensure that each topology is reliable. And yeah, of course, also links back to GitHub to find the source code. So yeah, if you want to check this out, if you want to use them in your project, that would of course be great. That would make me super happy. Or if you just want to check them out to like analyze the source code, look at what it does, look at the constraints, just to get some inspiration, get some new ideas for whatever you are working on, that would be great also. I mean, that is also one of the reasons that we're doing this open source thing, that we can all learn from each other. So yeah. But feel free to check it out. It will make me very happy. And with that, we have reached the end of the presentation. 30 minutes go by quickly sometimes. So final slide, you have once again the links to the website with documentation and to the GitHub with source code. And other than that, I would highly recommend you to check out my LinkedIn articles, because there I go into a lot more detail and a lot more discussion about the CDC and about their constraints and how we can write the constraints. A lot more details than what I could ever do in a 30-minute presentation. In the articles you will find analysis of the different topologies, discussions about constraints and how we make them reliable. There's also discussion about build tool settings, what we need to ensure in the build tool in order for our constraints to actually work, and a lot more. There will be more CDC articles coming, and I'm also going to write more articles about FPGA things. So you can use the URL, or this QR code will also take you to my LinkedIn. We can connect there, and you can find my current articles as well as future ones. And yeah, with that, there's nothing left to say except thank you for your attention and your engagement. This is an exciting topic, and I'm available for questions and also discussions at any point in the upcoming days. And yeah, please enjoy the rest of the conference.
Thank you, Luca.
Thank you so much.
Thank you, Luca, for this detailed presentation about clock domain crossing and your hdl-modules. Any questions for Luca?
Hello. Thank you, Lucas, for the nice presentation here.
There you are. Thank you.
If you come back to the first example you showed where you had this problem of the CDC.
Yeah.
Yes. Wouldn't it be enough, for example, to add some handshake signals and to build a sort of ready and valid in between the two clock domains instead of adding flops in the middle. Will this solution help? Did you try it out, or you discover maybe already some problem with this solution?
I think I missed the word. Can you say again?
If instead of adding a flop after the XOR, you add some logic to do some self-synchronization, some handshake signals, right, like ready and valid across the two domains.
Okay. Some logic for self-synchronization.
Exactly.
I mean, that sounds too smart for me. Well, I mean, maybe that works. Honestly, I don't know what that means. I think, I mean, things are possible to do with constraints on like the placement and the routing. Like, I'm not saying that it's impossible to make this work. I personally don't work with constraints like that. My general development philosophy is to leave as much as possible to the tool to solve. I think that's like the way a design changes over time and matures. Doing too much hands-on thing with the tool, I'm talking about like placement constraints and stuff like this, is a bad idea in my opinion. But it is possible to solve, to make this work with constraints and stuff like this, yes. I'm not sure exactly what you are meaning, but yes, it is possible. But no, I don't really know what self-synchronization and things like this mean. I'm sorry.
Okay. So maybe we can do a
we can talk later.
offline. And
Absolutely. I would love to talk later.
thank you.
Thank you.
Right. About your HDL modules, I see there are some constraints in your, for instance, with the CDC examples that you provide. But how do they work? Do you have? Are they like local to the synchronizer, or are they searching for the synchronizer or something? Because often the problem with constraints is that they work like on a global level.
Yeah.
And if you use, for instance, the Xilinx XPM, the constraints are somehow included in the things. Is that the case for your examples as well?
Yes, it is. And yeah, you mentioned XPM, and I was doing this before they were doing it, just to mention it. No, I'm joking. Yes, and the way that XPM are doing it is that they use what is called a scoped constraint, where I mean, if you know the tickle commands, the way that you load a constraint file is that you use read XDC. But you can do read XDC and then with the flag -ref. And then you write a name. If you're doing VHDL, it's a entity name. If it's Verilog, it's a module name. And that name has to be an entity that exists in your design. But when you load the constraint file like that, all the code, like all the calls in the tickle, get cells, get ports, they will be applied only to that entity. It will not search through the whole design, like deep and wide, the whole design. It will be applied once for each instance of all these entities. But so this is a way to make the constraint files a lot easier, because yeah, if I want the clock port of this CDC box, I can just do get ports clock and I will get it. Whereas, as you say, if we're doing a global constraint where we have to search the whole design, something like that, like yeah, I want to find the clock port of something that is 150 levels of hierarchy down. That is very hard. It gets very messy and it gets very slow on a big design. Whereas these scoped constraints, they're a lot faster and you can express the tickle, like how you find your cells in a much simpler way. Okay, thank you.
There is one question there and then in front.
Yeah. In general, I wanted to add regarding synthesis on FPGA, right? Like you explained here. I would like to have your opinion on using these timing analysis tools that also help here, right? on a professional tool like, Vivado and all, that you have to pay a lot compared to the open source uses, let's say, like PNR and all. Have you had any experience or with the open source FOSS tooling?
Yes, I have used Yosis to build things and to do formal also. I don't do it often. It's quite a few years since I did. I mean, Nina is in the audience. Maybe there's a better answer there. But I don't really know, like the way that I have written the constraints are, for most of them, with the standard commands. Maybe, probably. These work with the Yosis next PNR also. But yeah, it's just the fact of how this open source project grew, or how it was started and how it grew, and also my other open source projects that, like, I'm very happy if anyone else finds it useful also, and I put in effort to make the things as general and as useful as possible, but the main and primary reason is for my needs. And I have been, for 10 years, working exclusively with Xilinx and VHDL. So everything is VHDL, and I only verify it with Vivado, unfortunately. Thank you.
Last question, and then we need to move on.
So I have a question about your library of modules, HDL modules. Let's say that, okay, you are becoming an expert, very well known in your domain, and you'll get a very, very good job offer from a great company, and you'll accept this job, but the company will ask you to remove all your content from the web, because maybe it's doing classified stuff.
Yeah?
Yeah. Have you thought about using existing platforms like OpenCores or similar ones and put all your work over there instead of keeping your own website or your own account on GitHub?
I mean, I know of OpenCores, and I simply think that GitHub is a better platform for publishing these things and allowing them to get traction and for collaboration. What I do on my free time is none of my employer's business. It's my general approach, but I've been my own boss for quite a few years, so maybe I'm underestimating this problem. Like,
so we should make a backup of everything you have published on the CERN webs, on the CERN repositories.
That's all right.
So I just checked everything in the repository is like open source licensed, more or less. No, so in principle there is we can like fork it and modify it by ourselves.
Yeah, it's all to tie back to Javier's. It's all under BSD license. I own the copyright of everything, including things that are contributed by others, since it's a very good thing for the longevity and to be able to actually maintain an open source project. You have one person that owns the copyright. I own the copyright of everything. But it's under BSD license, and it's available. So, like, yes, fork away, use it as much as you want. If it's an open source project or public project or a commercial project, everything is possible with this permissive license.
Thank you.
Okay. Thank you, Luca. We can thank Luca again.
Yeah.